Thank you. Yeah, so this will be more of an advertisement of what Aeternity can do, not so much exactly how we do it, because, yeah, the word is fancy, and cryptography is, when you start looking at it, it quickly gets really, really hard. I'm by no means a crypto expert. I've read a few things, I've looked into a few things, I've implemented many things. I like it, it's fun, but it's really, really hard. And the guys that comes up with these protocols, they are really smart. So one should be careful. First, a quick word about me. Who am I? I'm an Erlang programmer, Erlang expert. I have a PhD in computer science. I did the PhD on testing and verification of programs. I've been programming Erlang now for 20 years. I had basically the same slide at the first Eternity universe, and it said 15 years. And that was an underestimate. 20 years is perhaps a year overestimated, but I should be fine. I've been part of the Eternity core development team since 2017, so almost from the start. I think only Ulf over there predates me in the core team, so one of the first around. And I've been doing Eternity. I've been involved in most of the stuff here and there. If you have questions or want stories about the background, feel free to approach me. What we're going to talk about here, yes, as I said, this will be an advertisement and somewhat of an introduction to some of the things you can do with Eternity. When it comes to cryptography, it's a terrible word. I agree. There will not be any complicated maths. That would take a bit too long. Maybe if I had the full 2 days, we could go into details. That would be really fun. But, I don't think there would be an audience, at least not after the first hour. And there will be some background, and I will try to explain a bit about what we're doing. First, a little bit of the basics. So all the blockchain stuff builds on cryptography. And there are some basic principles we need to agree on. There need to be a one-way function where you take something potentially large, you compute a number from that or a string from that, which is, you can take this big blob and you get the same number every time. If you take a slightly different blob, you get an entirely different number. That's a one-way function for you. We have elliptic curves, a fancy concept where you can easily add two numbers, you can easily multiply two numbers, but it's impossible to divide one number by the other, if we simplify it a bit. And this makes for a great setting where you can implement cryptography. You can implement functions where Alice and Bob or Charles and Diana have their own set of key pairs, and with the public key given away, and if I keep my private key, I have the private key, I encrypt something, I can give it away and show that I did indeed sign this by using these functions that clever guys in the past thought about, and we can just use them. So the main concept of the blockchain is that you can sign things. You can assert that I did produce this, and everyone can check that indeed the person who claims that he has this private key did indeed sign this blob or this piece of data or this transaction, which makes it possible for us to in a safe way on our little device, nowadays probably a mobile phone, you will create a transaction, you will input your secret stuff, and you will create a signature for that, such that anyone in the world, anyone on the chain, can then later verify that, yes, indeed it was Marco or Ulf or indeed me who actually signed this. And this brings all of this to us. We can build blockchains, and the concept, it's from the name, it's a chain of blocks, and we're using these one-way functions. So we take one block, we compute the hash of that, we put that hash in the next block, and we produce a new block, we compute the hash of that block, put it in the next block, and we have blockchain. And the blocks are signed by someone who produces them, And in the blocks are signed transactions and signed contracts. And there's also, in order to form a blockchain, we need some sort of proof of work or proof of stake, but let's ignore that for this presentation. There will be other presentations about that. And if you take the typical old style, or the first couple of generations of blockchains, everything is transparent, everything is visible. We do sign things, but that doesn't mean that things are encrypted. Things are signed. Everything is there in plain text. Everyone can inspect your transaction. Everyone can see whom you are transacting with or what asset you're sending from where to where. So everything is visible, everything is transparent. And this is nice until you actually don't want to be transparent and nice, and maybe you have something which you don't want everyone to see. And then we might actually, yeah, there might be something that you don't want everyone to see, that you want to put, but you still want to put it on the blockchain somehow. And that's a bit of a problem. So the underlying kind of idea here is, what if I can just prove that I know the solution of a problem without actually revealing the solution? It's kind of nice. I've come up with a very clever scheme for doing something, and I want to sell this to someone, but if I show them how I can solve the problem, well, they can just copy the solution and do it themselves. So in order to sell this, I have to negotiate with them and come up with a way to prove that I know how to solve a problem without actually showing the solution. And this is of course a problem which they have thought about in theoretical ways, in both the crypto world and also in the philosophical world. But the technical term when it comes to cryptography is zero knowledge proofs. And when they first came around in the 80s, I think, my history here is a bit vague, there were interactive proofs. So you had a series of challenges, and you had to answer the challenges, and if you answered enough challenges correctly, with statistical possibility, you were knowing the solution to the problem. This is a bit impractical if you want to do this on a blockchain, because a transaction is a transaction, that's one entity, and if you want to go back and forth, it would be extremely inefficient. So unfortunately, fortunately, there were more clever guys around that came up with evolutions of this, such that they could turn the interactive proofs into non-interactive proofs, where you can upfront decide on a starting point and provide the whole proof in one go, which makes it possible to actually put these nicely on the blockchain. And they have this really cute name. They are called ZK-SNARK. And the SNARK stands for, and I will read this because I can't remember it, it's Succinct Non-Interactive Argument of Knowledge. And the argument of knowledge part is the same as I just mentioned, that you prove that you argue that you have some sort of knowledge without revealing it. Because there's still the CK first, it says zero knowledge. But the important part for blockchain is the succinct and non-interactive. So succinct means that you can actually make it small enough, or at least efficient enough, that it fits in a transaction or in a block, and whatever you have. And non-interactive, as we discussed, that it can be done in one go. So at a high level, what you're doing if you want to use a zero knowledge proof on a blockchain, such as possibly Aeternity, there is a shared setup phase between the two entities, where you often publicly, actually, you both provide some public randomness, and you put that public randomness together and make a shared setup input string. And then you have a prover, which you are running on your little computer or on your little device, or maybe here it's a problem because the device might be a bit hot, because producing these proofs might be hard. Yeah, so you create a little proof, and then the idea is that there is a verifier, which is also again public. So you together create a problem which you agree on. This is the problem that you're supposed to solve. And whoever wants to interact with this verifier goes home, produces a proof. In that proof, there might be all of these secret sauce, all of the secret ingredients that you want to not reveal to the world. But when you can input them into your own proof, and then you create a proof. You publicly publish that proof, and there is this little verifier that can efficiently. Typically, you run this in a smart contract, or there's even whole blockchains which have this built in, like Zcash, Zcoin, and a few others. They rely on this entirely. That every transaction is basically a zero knowledge proof. But the idea is that, yeah, this verifier can efficiently conclude if the proof producer actually provided all the correct input. So you decide on a problem, typically a signature or I know a large number, and then you create a proof that you know this large number, and the proof that you're actually producing contains no trace of the actual input. And this is, to me at least, magic. I did try really hard to understand the magic or the mathematics behind all of this, but somewhere around the 2/3 of it I got really lost, and I kind of gave up and just took this for granted. There are nice libraries we can use. There are nice libraries where you can produce these little programs that you can put input into and check later that someone had the input for. So maybe I convinced a few of you that this might or might not be useful. I don't know. To me, at this point in my life, I realized, yeah, this is cute. This is very technical. This is very magic. Can you use it for anything useful? And then someone pointed me to the problem of tornado cache. Yeah. As so many pretty technical things, it's now banned. I know, but if we don't look at the financial government side of it, but the technical side of it, it's a magnificent piece of technology. They combine lots of different nice mathematical, technical concepts in a way, and they produce something which is almost, yeah, I could not have figured this out, but it's really cool. So the idea is that you have tokens on the blockchain, and remember, everything is visible, everything is transparent. You can see exactly who transfers tokens to who. And now you want to take those tokens and send them to someone without anyone knowing that you sent those tokens to that someone. And they came up with an idea for this. They made a service where you could input tokens and then at the later stage output tokens. And from the outside of server, there would be no way to connect the input to the output. And this is impossible if you think about it in where everything is public, everything is transparent. You can look at every contract interaction. You can, okay, of course you could write a contract that would send tokens around, but it would always be possible to just trace exactly where the tokens go. That's not a problem. So the trick they came up with, they're using zero knowledge proofs, they're using Merkle trees, they're using hashes, they're using one-way functions and whatnot. So, but on a high level, you take your tokens, you send them to a contract. Together with that contract, you add a note saying, it's basically a random string, but it's a note. And the contract will take this, they will put that note into a tree, and that's all that happens on the input side. But then, when you want to withdraw from this contract, you, along with your withdrawal request, you send a zero knowledge proof that says, I know how to construct one deposit note. I won't tell you which deposit note. I won't tell you what the note looks like. I don't tell you anything more, but that I know one of the nodes in the tree at this point. Who came up with this? It's ingenious and just crazy. But it works. And at least that convinced me that you can do useful things with zero knowledge proofs. Okay, but why were I looking at zero knowledge proofs? That's a great question, by the way. Many years ago, it's now 3 years ago, I think, I was given the task by someone, hey, we need cryptography primitives for zero knowledge proofs in Aeternity. So I was adding them. At that moment, I was working on the virtual machine for our smart contracts, smart contract language. So I was tasked with the task of just add these cryptography primitives there. And I did that, and I looked up a few online tests and some challenges. So I added a few tests for this, and I added it, and we put it in there, and we released it. It was, I think, 2 or 3 hard forks ago. And then afterwards I thought, but wait, what? We just added something. Why? Can you use it for something? Is anyone using it? So I had a look, and no one is using it. A year ago, there were 0 runs of this function that I had added on chain. Hopefully someone had tested it privately, but I don't know. But here we are, at least. Aeternity has zero knowledge proofs. We have what's known as BLS 12381. It's one of the curves for zero knowledge proofs. And we have had this, since here it says Iris hard fork. I think we added even 1 hard fork earlier. Unfortunately, I was also, while reading on this, I was prototyping Tornado Cache because it looked like a cute example. I wanted to understand it, so I implemented it. But it turns out there are a few other things you also need in the language to be able to do it efficiently. I could do a toy example with a tree that had the height of 2. So your contract could handle 4 deposits and withdrawals without it, before it was expelled or expanded. And with 4 people using a contract, the transparency argument or non-transparency argument is kind of out the door. So it's not really relevant, but next hard fork and you can start using your zero knowledge proofs. Though not for Tornado Cache, because that doesn't seem to be well received. Good. Sorry for being a bit unstructured here. There was a bit of a confusion when I posted the proposal of my talk. I suggested several things, and the title became a mismatch of all of them. But this is all I have to say about zero knowledge proofs. Are there any questions about zero knowledge proofs first, before I move on to multi-signature, which would be the second part?
Questions?
Thank you for your sharing. I have a question regarding the ZK proof applied in on-chain identity for privacy preserving this kind of scenario. So, can you tell me more how this could works in privacy preserving?
Yeah, it would be an application of using this. You would have to come up with a small program, and you would have to put this into a contract with some logic.
Yeah, for example, when a young teenager, when you want to check his age is over 18, allow him to buy alcohol in supermarkets. And for example, we work with a digital residency program, and we have a lot of concerns for users' privacy protection. So
this is the typical example of something you can do with a zero knowledge proof, that you provide a proof that you're over the age, but not revealing your identity. That's a typical thing that you can do with zero knowledge proofs. That's one of the examples. If you read about this, then this will come up as one of the examples. So yeah, I think that can be done.
Okay, thank you. So I just read the term you said. The verifier can be on chain. It means the issuers are for example, the government, and the verifiers on the chain. What do you mean, verifier? I
mean that you don't produce these proofs of zero knowledge on chain, of course, because then they would be visible, then the input would be visible. So what I mean there is that you do produce this binary thing, which is the proof of something. That's not done online, but you verify online that the proof is correct. That's what I mean there.
Okay, thank you.
Yeah.
Okay, thanks, Hans.
Yeah, so now on to something different, but related. Multi-signature. I think there was a presentation in the other room just before, which I unfortunately missed. Yeah, John is here even. And what I wanted to say here is that multi-signatures is a very multifaceted topic. Firstly, we have the two different kinds of multi-signature, where you have n out of n, i.e. 2 out of 2 signatures, where you have a group of people where everyone has to sign. That's computationally quite different from the case where you have a threshold of signatures needed, like if you have 3 out of 5 needs to sign something. Then there is the difference between making a naive threshold signature, where you just provide 3 signatures and you count them and see 1, 2, 3, yeah, that's bigger than or equal to 3. Fine, this signature is valid. Or you go the extra mile and compute an aggregated account for all the 5 signers, and then you do fancy cryptography to actually produce 1 signature, which you can verify. And all of these variants have valid use cases, and some of them are easier and just basically trade simplicity for a little bit of space or a little bit of computation. Typically in the world of transactions, if you add more signatures, well, the transaction will be larger, you will have to pay more, there will be slightly more data to store. Compared to if you can just use 1 signature, which is smaller and faster to validate. In the case of Eternity, we have picked, when we started Eternity, we picked a random, or not a random, we picked an elliptic curve called ED25519. And this curve is where we have our public keys and our private keys. And this curve and the signature scheme, EDDSA, have very nice characteristics. They are called Schnorr compatible, or they are Schnorr signatures. And this means that it's possible to do some of these fancy things out of the box, just as we speak. You can take a group of people and they can sign something together and they can aggregate that signature and in the end produce just 1 signature. And our blockchain would not know. So this is really cute. And there are a few different protocols for how you could do this. I think me and Dimitar actually proof of concept one of these naive schemes like 2 years ago or something, just to check that it actually worked. But this involved sending binary blobs back and forth, yeah, I think in 4 or 5 stages, and it was a bit complicated. We got it wrong a couple of times before actually managing, so it's not really very stable, but there are many protocols, many variants, again, with pros and cons. How many times you have to communicate, what you communicate, if you can communicate in parallel, or if it's a star pattern, or if it's a circular pattern. But I won't go into all these things. But lately, the community here seems to have agreed on that a protocol called Music2. That's a good way to do this. And this is for the case of n of n. So 2 of 2, 3 of 3, everyone signs. And it's a really nice schema. It consists of a setup phase where all the parties, they derive a key pair to be used for this aggregation. They also create a bunch of random data. And then all of that is sent around to everyone who is part of this signing group. And they compute together a public key, or everyone or anyone in the group can compute this public key. And that public key will then be just an account, it will be indistinguishable from any account. It will say AK underscore blah, 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 blah. And if you look it up in the Explorer, it will be an account. If you send tokens to it, it will be an account and whatnot. And then there's one round of, first, yes, they are indistinguishable, as I said. And also this is proved to be secure. That was my point, sorry. I went ahead of myself. So there's a proof of this. Again, yeah, clever guys, clever proofs, complicated maths. But they seem to agree that the proof holds. I can't comment on the proof. I did read is a strong word. I did look at it. And it seems plausible. There are Greek letters in there. There's lots of math, and probably fine. But what I'm coming to here is that there has been a couple of protocols before this one, which has been proven to have potential weaknesses. Not so much that they can be broken, but if you use them incorrectly, you will leak part of your public key, or part of your private key. Yes, so there's one round when you set it up, and then there's only one round of communication when you want to sign something. This is nice. So the group agrees on a message. Exactly how they agree, I don't know. And then they send this message to everyone. Everyone can compute a partial signature, and they send that back, and you compute a signature from that. That's very efficient if you have read a few of these protocols. They typically involve multiple steps. And you also have the last point here. You can also, from these partial signatures, actually tell who is not doing their work. So if you have all the partial signatures and you know who produced which one, you can also compute, is this a valid partial signature? And so you can pinpoint who is actually not playing the game nicely, which is nice. And this was my Christmas break thingy. So during Christmas, I played along with this. I made an implementation. It was almost finished back then. It is still almost finished. I had planned to finish it here at the Crypto Castle, but there were far too many interesting workshops the last couple of days. So I've been running around discussing with people and have not had time to finish. It's public anyway, it should work, but it's a bit rough around the edges. There's no introduction, and there are a few functions which are really missing, which should be there. But the general gist of it is there. And but this is just the cryptography. So in order to use this, you would need to figure out how to pass all the data around. Typically, you would add this to the wallet or a UI or something. Hey, I'm not the UI guy, so there will not be a demo, there will not be UI. So, this is what we have today. Next level, I just recently found this protocol. It's called FROST, Flexible Round Optimized Schnorr Threshold Signatures. And that seems to be the possibility to do T out of N in the same way, with an actual account, indistinguishable from other accounts, with one signature, indistinguishable from other signatures. But it looked pretty tricky. We'll see if someone comes along and picks up the challenge. I don't know, it looked a bit too hard for me, but we'll see. So, yeah, that's it on multi-signatures on-chain. And you've already heard about the contract-based one, so I think we have covered multi-signatures also. Questions on multi-signatures?